Okay, so today we're going to be talking about Extrema, and what Extrema refers to is basically maximums and minimums of a function on a given interval. So, if we look at any function, right, we'll just say from A to B, this doesn't really matter, but you know, so if we say some function like this, right, and we're looking at from here to here, and we want to determine the extrema, right? So that means we're going to be looking for the maximum values and the minimum values of this function on this interval. So first thing, we see this up here. This is the highest point this function reaches. So this is going to be our absolute max right there, right? And this right here, you can see that this is our absolute minimum. So that's the lowest point this function reaches. And now up here we see that the function goes and turns around. So this is what we call a relative maximum or local maximum. Either one works, right? And what determines a relative maximum is just whenever the graph turns around. And so if we had one of these, but we'll say, I don't know, that was really bad, but you know, if we had one like this where it turns around going the other way, this will be our relative minimum, right? So an important thing to notice is that maximums and minimums occur only when, okay, so I'll write this. Max and minimum occur either at endpoints or when the derivative equals 0. So what does this mean? So endpoints, if the function went like this at A, we can see that this is no longer an absolute minimum, but a relative minimum, because this point here on the interval is now lower. So our maximums and minimums, our extrema, can occur at the endpoints, because these can be lower than anywhere that the graph turns around, or higher in terms of a maximum. And same over here, if this graph ended higher than this point, that would be our absolute maximum at f of b. So that's important to know, that a maximum or a minimum can occur at the endpoints or when the derivative equals 0 or undefined. I should say that. So looking at this, we see everywhere that the graph turns around, we have either an absolute maximum or minimum or a local maximum or minimum. And if we think about this, if the graph of f of x is going up, that means it's increasing, and that means the derivative is positive, right? So it goes from positive, and then the instant where the graph turns around, the derivative equals 0. So that's f prime of x equals 0 at this point, because the derivative is positive equals 0, and then goes down and turns negative. So these can occur at where the derivative equals 0 or undefined. So say right here, instead of turning around, it came to a point and went up like that. Now we know that for a function to be differentiable, it can't have a cusp or a sharp turn in it. So this right here could also be a minimum or an extrema, because the derivative is undefined at that point. Right, and so let's look at this further. If we just analyze some graphs, okay. So we'll look at 3 graphs that will look very similar and decide where the extrema are. So we're just looking at from A to B, right? A b. We have this. We'll go up here, right? Okay, so we can see that our maximum can occur, if we remember, that'll be at the endpoints or where the derivative equals 0 or undefined. So we can see that this endpoint is going to be our maximum because that's higher than any point that the derivative equals 0 and the starting point. So this is going to be our max. And down here we can see right around here that's going to be our minimum because that's lower than the other endpoint. And now say if we had this right here, instead of a closed dot we had an open dot, meaning there's no function value at f of b, this minimum stays the same, so the minimum value of this function is still going to be right here, but we actually don't have a maximum, because if you may think that it's like right around here, but that's not true because you can get infinitely close to that point and it's still increasing, but you'll never reach that maximum value. And if we think about this, it can be at the endpoints, and f of a, that's obviously not our maximum because there's all this, and f of b doesn't exist, so we can't say that our maximum is at b f of b. So that's referring to this point here, right? We cannot say that this is a maximum because that's not a value that exists. And yeah, this stays the same as the minimum, right? And same thing for if we had an open dot here, we still don't have a maximum, and we also don't have a minimum either, because checking the endpoints, there's spots below it that exist, so this isn't a minimum and this is not a minimum. And now all we have to check are the points where the derivative equals 0 or undefined, and this right here does not exist. So that is not going to be our minimum because it doesn't exist as a point. So those are a few things that are important to know, that check endpoints, check where the derivative equals 0 or undefined, and if there's not a function value there, that is not a minimum or maximum, right? Okay. And there's a thing called the extreme value theorem. You don't really have to memorize this or anything. That just says on any closed interval, a function will have a maximum and a minimum if it is continuous. So from a to b, if you're looking at a closed interval, any function will have a maximum or a minimum, right? Wait, that's not true. Oh, yeah, it is true only if it's continuous. And if we look back to the reason why that didn't have a maximum is because it's not continuous all the way to the closed interval. Yeah, and same reason why the extreme value theorem doesn't apply here is because this is not continuous all the way. Okay. So if we had, and we won't always get a graph for this, so now we'll go over how to determine the maximum or minimums if we do not have a graph and we just have an equation, right? So we're given f of x equals 3x squared minus 24x minus 1. And we're on the interval 1 to 5, negative 1 to 5. So here we have to determine the maximum value and the minimum value of this function on this interval. So the first thing we do is check our endpoints. That's the easiest thing we have to do here. All right, we just plug in negative 1. We do this because we know our maximum or minimum, our extrema, can occur at the endpoints. So plug in 3 times negative 1 squared minus 24 times negative 1 minus 1. That's going to be equal to 3 plus 24 minus 1, minus 1, which is going to be 26. So we know that our leftmost point of this function on this interval is going to be at negative 1, 26, right? And now we got to plug in 5. So we do f of 5, and that's going to be 3 times 5 squared minus 24 times 5 minus 1. And that'll be 25 times 3 is 75, minus 24 times 5 is 120, minus 1, and that's going to be equal to negative 46, right? So we know our rightmost point on this graph, on this interval, is going to be at 5, negative 46, right? Okay, so now we checked our endpoints, but we also have to check wherever the derivative is undefined or 0. So to do that, we have to find the derivative. So we're given, I'll rewrite it, 3x squared minus 24x minus 1. So to take the derivative, use a power rule, that'll be 6x minus 24. Right? And so now we have to check where this is 0 or undefined. And the only time a algebraic derivative will be undefined is if it's a fraction. Like we'll say a over b or something. And this is only undefined when b equals 0, right? Because we can't have the denominator equal to 0. So it's the only time you have to check where the derivative is undefined is where it's a fraction and you have to set that fraction equal to 0. Okay, so we have to check where this is equal to 0. So to do that, we just set it equal to 0. So we have 6x minus 24 equals 0. And from then we can just determine that x equals 4. Bring 24 over, divide by 6. So x equals 4. Now what does this mean? That means when x equals 4, this graph has a derivative that is equal to 0. And that means that this graph will like turn around, right? So this like point here has a chance to be our absolute minimum, or yeah, our absolute minimum or absolute maximum. So here, now we have what is called a critical value. And that's where extrema can occur on a function. And it's entirely possible that this value is somewhere in between the two, like in between this -1 and 5. Or I should say this 26 and negative 46. It's entirely possible it could be 0, right? And so we have to remember not to plug this back into the derivative, because that'll just give us 0, because that's what we just solved for. We want to plug it back into the function value, or back into the function to get the value at x equals 4, because that's possibly our maximum or minimum. So f of 4, we see 3 times 4 squared minus 24 times 4 minus 1. So that'll be 16 times 3 is 48 minus 96 minus 1, which is going to be negative 49. So that tells us that we have a point at 4, negative 49, and that is a critical value because that's where the derivative equals 0 at that point. And looking at these, we can determine our maximum and minimum values on this interval just by looking at the y values, right? So from here we can see this is going to be our maximum on the interval, obviously because this 26 is greater than these two. So we have absolute max at -1, 26, and an absolute minimum we can determine from the other two to be this point right here at 4, negative 49, because that negative 49 is less than this negative 46. So what we just did is called the first derivative test. That's when we set the derivative equal to 0, find the critical values, which is where the derivative equals 0, and plug those back into the original function to determine whether or not that's an absolute minimum or maximum. Right? And to make sure we understand this, we'll do another example. So for this one, we're given f of x is equal to 3x to the 2/3 minus 2x plus 1. And we are looking at the interval from -1 to 8. And for this one, we're going to do the same thing as the last one. So we know our extrema can occur at the endpoints, so that's what we check first. So we check f of -1. It's going to be 3 times -1 to the 2/3 minus 2 times -1 plus 1. And that'll be 3 plus 2 plus 1. So that's 6. So our first point that we have is -1, 6. Right? And so now we also have to check this 8, because our extrema can occur at the endpoints. So that'll be 3 times 8 to the 2/3 minus 2 times 8 plus 1. And we know, and just a quick recap, if you have like a to the 2/3, that'll be equal to the cubed root of a squared, right? Any number to some fraction b over c, that c is going to become the root of the root, and then the numerator of that fraction is going to become the exponent. That's just how to do fractional exponents. So this 8 to the 2/3, we can see that as the cubed root of 8 squared. So the cubed root of 8 is 2, and 2 squared is 4. So we have 3 times 4 minus 16 plus 1. So 3 times 4 is 12, minus 16 is -4, plus 1 is -3. Right? So that's our second point at 8, -3. Right? So right now, this is our maximum and this is our minimum on this interval, but we also have to check where the derivative equals 0. So to do the derivative, we have, I'm just rewriting this so it doesn't get confusing. So the derivative, using the power rule, is bring this down 3 times 2/3, it'll be 2x, and then we subtract 1 from this to the -1/3 minus 2. And again, what we do here, set this equal to 0 and solve for x. So we have 2x to the -1/3 minus 2 equals 0. And from here we can get 2x to the -1/3 equals 2, x to the -1/3 equals 1, and that tells us that x equals 1. Right? That x equals 1 is where the derivative equals 0, and that is the only spot on this interval where the derivative equals 0, right? And again, this -1/3, that'll be -1/3, that is going to be equal to 1 over the cubed root of x, and we see this is only equal to 1 when x is equal to 1. That's how you go from here to here. Okay, so we have this, our critical value, our critical point. And what we do here is plug this back into our function to see if it's our minimum or maximum. So f of 1 is going to be 3 times 1 to the 2/3 minus 2 times 1 plus 1. And so this will be 3 minus 2 plus 1, which is going to be equal to 2. And so that tells us we have a point on this function at 1, 2. And from here, we have our points, our endpoints, and our critical values, and we can determine our maximum and minimum to be the maximum at -1, 6, because that 6 is greater than these two, and our minimum at 8, -3. is this -3 is lower than these two. And that is an example showing that sometimes the critical values are not your extrema, right? They're not your absolute extrema, because this was still in between these two endpoints, right? And so all you need to remember about finding absolute extrema on an interval is to check the endpoints and then check the critical values. And critical values is taking the derivative of the function, setting it equal to 0, and plugging that value back into the function. Right, and that's going to be it for this video. And for extra practice, these ones are a little, well, this first one's kind of the first one we did. If you want to try these on your own, we have 6x cubed minus 6x to the 4th plus 5 on the interval -1, 2. Right, and another one to try could be sine squared x plus cosine x on the interval 0 to 2 pi. I don't know if the notes are the same this year. These come straight from the notes. So this is just some extra practice. If you don't quite get the grasp, I would start with this one. This one's definitely going to be the easier one. And yeah, if you have any questions, let me know. Just endpoints and critical values are your only things you have to check for the extrema. And just plug those values back into the function, and that's how you determine the maximum and minimum of the extrema on an interval.